section. And the first team presenting is Aerocounters, team number 4. The customer is Professor Toggle.
We're Team Aerocounters and Hilary. This is Rick, Gavin, Jeff, and Hugo. So a little background on what we are doing. White nose syndrome is characterized as a condition of hibernating bats. And it was named for the fungal growth that can be seen on the muzzles and ears or wing membranes. Affected bats exhibit abnormal behaviors in hibernation, including movement towards the entrance of caves or barns where they live, as well as daytime flights during winter months when food is scarce. So during hibernation, they are out looking for food and moving when they should not be. These abnormal behaviors contribute to the untimely consumption of stored fat reserves, causing emaciation. The characteristic documented in a portion of bats that die from this disease. White nose syndrome was first documented in February 2006 in Albany, New York. Since emerging in the northeastern part of the United States, it's been confirmed in 20 different states as far-reaching as Alabama, Iowa, and Missouri. Current bat populations surveyed in the Northeast estimate declines in excess of 80%. The sudden and widespread mortality associated with disease is unprecedented in hibernating bats, among which disease outbreaks haven't been previously documented. It's also unlikely that the species of bats affected will recover quickly, considering that they are long-lived and produce usually only 1 pup per year. So even in the absence of disease, bat populations don't fluctuate widely in numbers over time. Worldwide, bats play critical ecological roles in insect control, plant pollination, and seed dissemination. The decline in North American bat populations will likely have far-reaching ecological consequences. The task we're presented with was to design a device that could actively monitor the flow of bats at the point of entry and exit. In our specific case, the 2 locations our customer intends to deploy our prototype are in small barns pictured here. The windows you can see right here, this is the inside and outside of the same barn. This is much smaller, and this barn here, this window is about 3 feet high and 2 feet wide-ish. These 2 locations are home to maternal bat colonies from about mid-May to mid-September each year. Although bats migrate to warmer climates during cooler months, our device is intended to remain there year-round. The sensor array we designed to monitor bat activity consists of 4 40-inch pieces of extruded aluminum, creating a square grill you can see here that we have outside for demoing as well. Each vertical aluminum piece houses 16 photodiodes and 16 LEDs, effectively creating 2 parallel planes separated by 1.5 inches. So you can see here we have right here the photodiodes and here the LEDs, and they line up. These ones line up correspondingly on this side, so we have 2 parallel planes going on. So they're each LED and photodiode are housed in an acrylic base that we designed that holds dip sockets. The photodiodes and LEDs, obviously, we didn't want to solder anything in because we wanted to make it easy for for the end user to be able to replace those elements, once it goes out. All other hardware, including the PCB and battery, are housed in a Neem 4 weatherproof project box intended for year-round outdoor use. It's not pictured here, but it's outside for use later.
All right. So the array. So as we can see, here see an overview of the design. We have the sensor array and a lot of electronics that will take the inputs and outputs of the sensor array and output them into a microprocessor. The microprocessor will then feed some wireless module, which will send information to some website, which will update the database on a real time. So we're going to take a brief look at how the hardware in this project works. We start off with 12 volts coming from a rechargeable lithium iron phosphate battery. We chose the lithium iron phosphate battery because of its high lifetime. It's about has about five times larger lifespan than a standard SLA, which is about 2,000 cycles of power, full power to drain. These 12 volts are then fed into a buck converter, which scales down on the voltage to 3.3 volts to be used by the rest of the components in this in the whole system. The only exception would be our wireless module, which uses 4 volts, which we have a separate secondary converter, which will scale from 12 volts to the 4 volts that we need. The sensor array is connected via standard wires to the PCB, and during operation, only 2 LEDs and photodiodes will be operational at any given time. What we mean by this is that what's going on here, as you can see, is that our microcontroller or microprocessor is controlling these muxes and demuxes. And what these muxes and demuxes are doing is they're basically targeting certain photodiodes and LEDs. Basically what's happening is, if you can imagine the two parallel planes, we will have an LED and a sensor or photodiode that will light up and sense at the same time. And we will go down the frame one by one. This is done to conserve power because we don't want all the LEDs turned on at the same time. There are 32 LEDs and 32 photodiodes in all. And each photodiode is connected to a voltage current amplifier, current to voltage amplifier, which will take the current produced by the light that it receives from the LED, and it will amplify into a voltage, which can then be read by the microprocessor to determine if an object is there or not. An object is determined to be there if the light doesn't pass all the way through. It is blocked. The photodiode won't receive the light, so we know something's in the way, and we will go on from there. And like I said, all these outputs and inputs and outputs will be then fed into the microprocessor, which will through UART send its information to a wireless module that we have connected. The wireless module is intended to will send out a message out to some outside server using an SMS message.
So this entire system is going to be deployed in some fairly remote areas. Hence, we're also going to be using a solar panel and the battery that Hugo was just talking about. And also, this is the same reason why we're using SMS over GSM bands rather than, say, Wi-Fi or Ethernet or something to talk to our server. So just a little bit about another concern for power consumption. It's been a big part of this project. Our device runs in an active and passive mode. The active mode is, it depends on the habits of the bats throughout the summer. The active mode can be about 2 1/4 to 3 1/4 hours, depending on the given month. We have a few protocols to configure the device those times remotely, because the user is really never going to interact with the device in person, but rather through the website. There's no UI on the actual Aerocounter. So we're sending, as well as this configuration data, more importantly, over the GSM bands is the updates to our server on our bat count. We're going to be sending these updates approximately once a minute, and just showing a live feed whenever we are sampling. So our detection algorithm for our bats here is fairly simple, actually. Before I get into that, though, I'd like to show you at least a little bit more context of what we're trying to see here. It's a kind of long video, but I'll just show a brief bit of it. So this is a IR cam looking at the Lincoln site, the Paxton site, and you can see those quick little guys scurrying through are obviously the bats. And you can see the window on the left side of the screen here. So just to get a general idea, you may have noticed one just flew out. Kind of hard to see because they are going pretty fast. I won't wait for another, but you get the general idea. This is really the problem we're going to solve, and our array is going to be mounted on the inside of this window here. So in order to detect these bats coming through the frame, and in this very small power concerned embedded system, we're just using a simple state machine. Imagining the bat coming through the 2 parallel planes, we first start the state machine at a given node. By node, I mean a pair of an LED and a photodiode. Once one is obstructed, we realize that something's starting to enter the frame, and we wait for the next plane to be obstructed. We then wait for the first plane that was obstructed to not be obstructed, and then the last plane to not be obstructed. So a full pass through. And any exceptions to that rule, we throw it out, forget about it, and start cycling again. And we also have a timer running throughout all of this. We didn't want to draw, all the actual lines that should go into this state machine going back to state 0 because it's really messy. So we do have a timer going through all of this. So if an object's coming through too slow, we don't want that to trip it. So for example, while it would be fairly impractical for a moth to trip our system, the moth is flying perfectly through. It flies at much slower speed than the bat. These low ground bats in particular. So things like a moth would not be triggering this system. So then on the other end, we have our website. Extremely simple. Our website really is just the front page is a login showing a live feed. Right now we just have dummy data existing there because it hasn't been deployed yet. It's over right down the hall, not in the bat barns. And there's a simple login that's going to be given to our client so that he can access the more advanced features such as sending messages to the device to configure it, searching the database. If, for example, he maybe wants to get some information about bats activity and wants to plot any sort of trends, he can get sort of information from there. We don't do the plotting, just to be specific. We can just give him the raw data. And if our client, being a professor, wants to have some grad students do his work for him, he can create some accounts. So here's just an example of searching the database. We have this example set up outside for you if anyone wants to mess around with it later. You can search by date, by the status of the sample, by the number of bats in and out, and simple, very simple things going on here. Just search and enter the fields and you'll get some good stuff back to you. So it's pretty much what we got. If anyone has any questions, feel free to answer.
I have a question about the two planes you were talking about. So, I mean, what are they? Is it one plane is the LED ones that are detected?
So we actually have, each plane is identical, we just have them switched. So on one side you have photodiodes, and the other side you have, thanks. So here you have photodiodes, which line this side, and then, so we call the back side of this frame X, and the front call it frame Y. Each side we have obviously pairing, and the purpose of the two planes is just simply so that we can determine which direction it's flying in or out. And we also, just something to mention, the reason, in addition to power consumption, the reason why we want to just have one node on at a time, also simplified our algorithm for detecting a bat, because we didn't have to worry about crosstalk. For instance, if an LED down here was on and this photodiode sensed a drop, but it only came from here, we didn't want to have to worry about that. So right now, we only detect horizontal, like one-to-one breaks, because only those two are on at any given time.
Yep.
Speaking of that, what is the cycle time for the LEDs and detectors?
The cycle time. The cycle time is, we actually had to take a lot of care to keep our algorithm very simple and to configure our ADC and the microprocessor to be in sampling and holding for a short amount of time, as well as take a few samples on a given instance, because there was a little bit of noise, there was a little bit of transient effects. So our actual frequency from, say, to get from one LED pair, or LED photodiode pair, all the way around and back, which is the more important part, because if the bat's coming through, yeah, exactly, you want to hit again, is right around 300 hertz. So it's fast enough to pick up a bat going at about 20 miles per hour. And the documentation we've seen about little brown bats has varied slightly, but the highest numbers we've seen for little brown bats, and that's flying in the measurements they use is essentially down a straight hallway as fast as they can is around 21 or 22 miles per hour. So if they're going as fast as they possibly can, completely wound up, we might miss them, but it's not the typical case. The typical case is in the teens.
And then you also mentioned active and passive modes. What's the difference?
So in the passive mode, the microprocessor is, the wireless chip is completely shut off. And the microprocessor is in its lowest power mode, running on an auxiliary clock. The active mode, we have everything on, waiting for text messages, sending text messages every minute, and doing all the cycling. Yeah.
You guys thought about maintenance for on the frame? So imagine the market's pretty dirty if one of the sensors was gone.
One thing we did in the design of this also, in addition to it just being weatherproof, the weatherproofing isn't included when we took this picture, but we only have the LED and photodiode going vertically. We originally wanted it to be going in 2 dimensions horizontally as well, just for increased accuracy. But not only would that slow our runtime down to cycle all the way around, we would have problems with things collecting on the bottom. So we have it pretty sealed off from water and all elements. So as long as it's mounted appropriately, like a pretty heavy picture frame, just on the studs, it's about 48 pounds. It's not too heavy, but heavy enough. It can hang out there for a pretty sustained amount of time.
Yeah, if you notice outside, we have this complete, everything's sealed off, especially the photodiodes and LEDs. They're kind of like a homemade bulb.
Yeah, all the wiring is now
hidden. Yeah.
So I guess this is also another maintenance question. It seems like ideally you should not have to touch that, I guess, the entire season that bats are coming in and out. Do you have any way of checking on sort of the status of this? Like, do you have any way of checking the battery life, maybe through your web application, or even like how long it's been on, or do you have any access to that information?
So these are two things that we had planned. They're not implemented yet. One is to check the battery over an AEC line in the microprocessor, and the other one is to essentially just run a cycle through and take ADC readings as essentially the same input to our algorithm, and see if an ADC reading is especially low or just completely out. If that's the case, then and we're assuming that while this is running, it's in maybe a time that we'd rather be passive, we assume nothing's blocking it. We can then report back, send a text message back saying, oh, LED 16 is out, or LED 12, LED or photoed out. There's really no way of us knowing LED or photoed out, but we can know suspects, alert our client and say, hey, you might want to check this one out, it might be affecting your data.
What wavelengths are your LEDs at? Do you know if it bother the bat or
The wavelength is 850.
It's 850 nanometers, which puts it in the infrared range. So that we picked the infrared so that it wouldn't actually bother the bats.
Did you guys get a chance to do any testing to see whether it was as accurate as you hoped it would be?
The testing we've done has not been with bats, no, in particular. And we really haven't gotten our hands on a radar gun or some, super nerf shooter. So most of the testing we've been doing is throwing like stuffed animal through. We've been throwing it extremely hard, very slow, like lobbing it through at a speed that we don't want to detect, and it's getting what we like to see. Yeah.
Sorry, I may have missed part of the conversation at the beginning. You said that it only detects individual bats. And I'm assuming there's a reason for that, so when the bat cave empties out or fills up with all of them coming in or going out, that's of no interest.
Yeah, we don't actually, it was specified to us that we don't need to account for multiple bats at the same time, mostly because, one, it's so rare, and as you can see in the video, because they're flying so fast, and the window itself is not enormous, that's not something that we need to account for, actually. It's so rare.
And out of curiosity, did you consider using the ultrasound of the bats as a sensor to wake up and put your system to sleep?
Did not consider that, no.
Okay.
Fairly interesting idea, though.
You're using IR, LEDs, and photodiodes. How difficult was it to get proper alignment so you can't see the light?
It was actually not terribly challenging because the range of light that the LED was putting out was such that, it was at least probably a foot where the photodiode could detect it at this distance, about a meter away. So as long as we just make sure that we only have one node on every single second or whatever moment, we could always make sure that that was what we were registering. So the alignment was, although we wanted to make it as as precise as we could, it wasn't necessarily down to like the millimeter. We just wanted it to visually be aligned, but yeah, it wasn't an issue.
And one other question, presumably the bats are moving in and out during dusk times. Does your system have any interference with things like sunlight or straight line? It's causing a problem.
Well, we plan on mounting it for one inside the barn window. However, if we do shine a flashlight directly at any individual photodiode, we can't get a reading off of that because basically we're setting the signal so high and it's detecting differences. So that would be a problem, but because we're putting it inside the frame or inside the barn, we don't really have that issue. And even at the other location, or both locations, if it was inside, obviously it makes it less prone to the elements. But outside, there's also even still the roof extends a little bit to create a little bit of a paint, but it's not too much.
And we're also oversized of the window, so that we're not going to be at the very edge of the window where somebody might be able to reach and put it out. Oversized by a lot.
But considering we're also sampling at dusk time, we wouldn't really have to worry about bright direct light anyway.
Yeah.
I guess on that note, have you thought about the infrared spotlights from the camera? Is that something?
I think
Or
not
is it
necessarily. We're considering the purpose of our prototype is to replace that camera that's there.
Okay, thank you.